Floating point numbers. Going beyond signed and unsigned numbers, programming language supports numbers with fractions, which are called real in mathematics. Here are some examples of real numbers. Minus 2.34 into 10 to the raised 56. Similarly, the pi number 3.1415965 or epsilon number 2.71828 or 0.00001. These are some examples of real numbers. In some cases, the number did not represent a small fraction, but it was bigger than we called represent with a 32-bit signed integer. The alternative notation for these numbers is called scientific notation. In scientific notation, it has a single digit to the left of the decimal point. A number in scientific notation that has no leading zeros is called a normalized number. Normalized number is the usual way to write it. For example, 1.0 into 10 to the raised 9 minus 9 is in normalized scientific notation. But 0.1 into 10 to the raised minus 8 or 0.0 into 10 to the raised minus 10 are not a normalized numbers. In this slide, we see that minus 2.34 into 10 to the raised 56 is a normalized number. On the other hand, 0.002 into 10 to the raised minus 4 or 987.02 into 10 to the raised 9 is not a normalized number. Just as decimal numbers in scientific notation, we can also show binary numbers in scientific notation, which is 1.0 or 1.xxx and to give power to the exponent y. The binary number in the normalized form, we need a base that we can increase or decrease by exactly the number of bits. The number must be shifted to have one non-zero digit to the left of the decimal point. Only a base of 2 fulfill our needs. Since the base is not 10, we also need a new name for the decimal point. Now we call this decimal point as a binary point. Computer arithmetic that supports such number is called floating point because it represents number in which the binary point is not fixed as it is for integers. The programming language C uses the name float for such numbers just as in scientific notations. Numbers are represented as a single non-zero digit to the left of the binary point. A standard scientific notation for reals is in the normalized form offers three advantages. It simplifies exchange of data that includes floating point number. Number two, it simplifies the floating point arithmetic algorithm to know that number will always be in this form. And the third point, it increases the accuracy of the number that can be stored in a word since real digits to the right of the binary point replace the unnecessary leading zeros. The representation of an LEGV version 8 floating point number is shown as -1 used for signed number, f for fraction, and 2 over exponent, where s is the sign of the floating point. 1 means negative and 0 means positive. Exponent is the value of the 8-bit exponent field, including the sign of the exponent. And fraction is the 32-bit number. As we already seen in chapter 2, this representation is also called sign and magnitude representation of binary numbers, since the sign is a separate bit from the rest of the number. In general, floating point numbers are of the form -1 over s into f into 2 over e. F involves the value in the fraction field and e involves the value in the exponent field. These chosen size of exponent and fraction gives LEG version 8 computer arithmetic and extraordinary range. Fractions almost as small as 2.0 into 10 over minus 38, and number almost as large as 2.0 into 10 over 38 can be represented in a computer. Also, extraordinary differs from infinites, so it is still possible for numbers to be too large. Thus, overflow interrupts can occur in floating point arithmetics as well as in integer arithmetics. So, an overflow in floating point numbers occurs when a positive exponent becomes too large to fit in the exponent phase, and it raises exceptions. Also, there is an underflow in floating point. It occurs when a negative exponent becomes too large to fit in the exponent field. It also calls an interrupt. One way to reduce the chance of underflow or overflow is to offer another format. This number is called double and operates on doubles as called double precision floating point arithmetics. Single precision floating points is the name of the earlier format. The representation of double precision floating point number takes one LEG version 8 double word, where s is still the sign of the number, exponent is the value of the 11-bit exponent field, and fraction is the 52-bit number in the fraction field. These single precision and double precision formats goes beyond LEG version 8. They are part of the IEEE 754 floating point standard, found in virtually every computer invented since 1980. This standard has greatly improved both the ease of porting floating point programs and the quality of computer arithmetics. To pack even more bits into the number, IEEE 754 makes the leading 1 bit of normalized binary number implicit. Hence, the number is actually 24 bits long in single precision and 53 bits long in double precision. To be precise, we use the term significant to represent the 24 or 53-bit number that is 1 plus the fraction. And fraction, when we mean the 23 or 52-bit number, since 0 has no leading 1, it is given the reserved exponent value 0 so that the hardware would not attach a leading 1 to it. So 00000 binary number represents 0. The representation of the rest of the number uses the form from before with the hidden 1 added. The representation of the rest of the number as minus 1 over s into 1 plus fraction into 2 over e, where the bit of the fraction represent a number between 0 and 1 and exponent specifies the value in the exponent field to be given in uh, for example, if we have a number with the bits with the fraction of with the fraction bits from left to right as s1 s2 s3 so on, then when we convert them back into decimal we write it as minus 1 over s into 1 plus s1 multiplied by 2 over minus 1 plus s2 multiplied by 2 over minus 2 plus s3 multiplied by 2 minus 3 plus s4 multiplied by 2 minus 4 and so on into 2 over exponent. The figure here shows the encoding of IEEE 754 floating point number standard. Other features of IEEE 754 are special number symbols to present usually events. For example, instead of interrupting on divide by 0, software can set the result to a bit pattern representing plus infinity or minus infinity. The largest exponent is reserved for these special symbols. When the programmer prints the result, the program will output an infinity symbol. For IEEE 754 even has a symbol for the result of invalid operations such as 0 divided by 0 or subtracting infinity from infinity. This symbol is NaN, which means not a number. The purpose of NaNs is to allow programmers to postpone some tests and decisions to a later time in the program when they are convenient. IEEE 754 also represent that floating point represents that could be easily processed by integer comparison, especially for sorting. This desire is why the sign is in the most significant bit, allowing a quick test for less than, greater than, or equal to 0. It is a little more complicated than a simple integer sort, since this notation is essentially sign and magnitude rather than 2's complement. Placing the exponent before the significant also simplifies the sorting of floating point numbers using integer comparison instructions. Since numbers with bigger exponents look larger than numbers with smaller exponents as long as both exponents have the same sign. Negative exponent poses a challenge to simplify sorting. If we use 2's complement of any other notation in which negative exponent have a 1 in the most significant bit of exponent field, our negative exponent will look like a big number. For example, 1.2 into 2 to the power minus 1 would be represented in a single precision as all zeros from 0 to 22 bits, then all ones for 23 to 30 bits, and 0 in the 31 bit because 1.0 is a positive number. Remember that the leading one is implicit in the significant. The value 1.0 into 2 over plus 1 would look like the smaller binary number in single precision as all zeros from 0 to 22 bits, then a 1 in 23 bit, and all remaining bits are 0. The So this is the table uh, as exponent fraction which is we used for converting floating point numbers into IEEE 754 floating point format. In this table, S represent a sign bit for single precision numbers as well as for double precision numbers. It is 1 for negative represent a negative number and a 0 represent a positive number. Then there is an exponent. In single precision, exponent field is 8-bit wide, and in double precision, the exponent field is 11-bit wide. Similarly, for a single precision number, fraction field is 23-bit wide, and for a double precision number, the fraction field increases up to 52 bits. So the total number of bits in single precisions including sign, exponent and fraction is equal to 32 bits, and for double precision number it is up to 64 bits. And the below table where x is equal to minus 1 over s multiplied by 1 plus fraction multiplied by 2 over exponent minus base is used for converting an IEEE 754 floating point number into a normal floating point number. So IEEE 754 uses a bias of 127 for single precision. So an exponent of minus 1 is represented by the bit pattern of the value minus 1 plus 127, which is equal to 126 and which is equal to 0 1 1 1 1 1 1 0 in binary, and plus 1 is represented by 1 plus 127 or 128 is equal to 0 0 0 0 0 0 0 1 into the binary. The exponent bias for double precision is 1023. Biased exponent means that the value represented by a floating point number is really minus 1 over s into 1 plus fraction multiplied by 2 over exponent minus bias. The range of single precision number is then formed as small as plus minus 1.00000 into 2 over minus 126 and as large as plus minus 1.11111111 up to 32 bits into 2 over 127. Let's understand it with an example. Let's have an example. In this example, we want to show the IEEE 754 binary representation of the number minus 0.74 in single and double precisions. So first of all, we convert decimal number into binary number and we get minus 0.75 is equal to minus 0.11 in binary. So as we see that this is not a normalized number, so first of all we convert it into its normalized form and we get it as minus 0.75 is equal to minus 0.11. After normalizing it, it becomes minus 1.1 into 2 to power minus 1. Now we clearly see that we move the binary point towards our right so that there is a 1 in the leading position. So the general representation for a single precision number is as given minus 1 over s into 1 plus fraction into 2 over exponent minus 127, and we write this number into this form. We get minus 0.75 is equal to minus 1 over 1 into 1.1 into 2 over minus 1. So now we calculate our fraction, exponent and sign bits. As minus 0.75 is a negative number, so sign bit is minus 1 is equal to minus 1. Now for the fraction part, we use 1.1. And we in this particular number we have only 1. We take only 1 from the right side of the binary point. So there is so our fraction becomes 0.0000000 up to a single 1 in 23 bit. And we calculate our exponent as in after normalizing our number, we have minus 1 into the exponent. So we add this minus 1 into 127 because IEEE 754 use a bias of 127 for single precision. So we add this minus 1 into 127, which is equal to 126. Now we convert 126 into 8 bits, which is equal to 0 1 1 1 1 1 1 1 0, and we put this 0 1 1 1 1 1 1 1 0 into the table between 23 and 30 bits. And IEEE 754 use a BICE of 1023 for double precision. So for double precision, we add -1 into 1023 and we get an exponent of 1022, which is equal to 0 1 1 1 1 1 1 1 1 1 1 0, and we put these 11 bits into the double precision table. So in this slide you see on your left, on your right below corner, there is a table for single precision and there is a table for double precision. For single precision, you may clearly see that there is all zeros from 0 to 21 bits and there is a 1 into 22 bits. And from 23 to 30 bits, we replace our exponent 0 1 1 1 1 1 1 0, and the 31 bit is for signed representation, and as we have a minus number, so we put 1 here. Similarly, for the double precision number, we have all zeros from 0 to 11 bits and there is only a 1 into the 19 bit, and we have an 11 bit exponent between 20 to 30 bits and a sign bit into the most significant bit, which represent that this is a negative number. So if we want to convert a given number back into a normal floating point number, for example, we have a number 0 0 0 0 0 0 0 0 0 up to 1 0 1 0 0 0 0 0 0 1 1. So first of all, we have a leading one, I mean most significant bit is 1, which tells us that this is a negative number. Then we have a fraction bits. For single precision, first 23 bits are used for fraction, and we separate these fraction bit from the given number, and the remaining 8 bits represent exponent, and we also separate them from the given number. So our fraction becomes 0 0 0 0 0 0 0 0 1 0. Now we convert this fraction back into the binary number, given 0 multiplied by 2 की power -1 plus 1 multiplied by 2 की power -2 plus 0 multiplied by 2 की power -3 plus 0 multiplied by 2 की power -4 2 की power -4 plus so on up to 2 की power -22. So as there is all zeros, so we have only 1 in this fraction, and it is becomes equal to 1 multiplied by 2 की power -2, which is equal to 0.25. Similarly, we convert our exponent and we get 129, because the binary of 100001 is equal to 129. So we put this into our previous table, which is x is equal to -1 over s multiplied by 1 plus fraction multiplied by 2 over exponent minus BICE. So we put our values in this table. We get x is equal to -1 over 1 into 1 plus fraction is equal to 0.25 multiply by 2 over exponent minus bias. Now our exponent is 129 and our bias for single precision is 127, and we get 129 minus 127. After simplifying it, we get minus 1 multiplied by 1.25 multiplied by 2 over 2, so it becomes minus 5.0. So there are some special cases in IEEE 754 standard. Uh, in first case, if we have an exponent with all ones and a fraction part with all zeros, this represent a infinity number and can be used in subsequent calculation avoiding need for overflow check. In second case, if we have all ones in exponent field and are non-zero in the fraction part, then it is not an infinity number, but it represent an NaN, which means not a number. It indicates illegal or underdefined result, for example 0 divided by 0. Interpretation of IEEE 754 floating point numbers. This some typical cases of IEEE 754 floating point number, and these are reserve cases. For example, for a zero, if we represent a zero number in IEEE 754 floating point number, then sign, exponent, and significant all bits are 0, 0, 0, 0. If we have a 1.0 number and we represent it in IEEE 754 floating point uh, standard, then we have as then 1.0 becomes uh, as it is a positive number, this becomes 0 for sign bit, and its fraction point has all zeros and its exponent is 1 1 1 1 1 1 1 and 0. Similarly, if we have a minus 1.0, then our sign bit becomes 1 and significant bits remains all zeros, and our exponent remains same as 1 1 1 1 1 1 1 and 0. Only sign bit changes from 0 to 1. For a positive number or for a positive infinity or a negative infinity, we have all zeros in fraction uh, part and all ones in the exponent field, and only a sign bit change for positive or negative representation 0 or 1. Similarly, for not a number representation, we have all ones in exponent field and we have 0 or 1 in sign field, and we have non-zero bits in the significant bit.